thank you all for being here. Thanks to the organizers for accepting my presentations. It's like an honor for me to be in front of you and on this stage. We'll talk about a serverless Kafka architecture for timely earthquake notifications, basically how a project, like in cloud, can be used like in combination with different programming abstractizations, different technologies, to achieve, to work, or at least a goal, towards a goal to save lives. Who am I? I'm Vlad Onetiu, basically from Cluj-Napoca, city in Romania. If you heard about Vlad the Impaler, that's the region, Transylvania. It's also called like the Silicon Valley of Romania because of the fast-growing technology kind of things. I'm working in cloud development, cybersecurity, projects in data science domain, basically from, let's say, extraction of data, modeling of the data, and also trying to create multiple projects, like final projects, which could bring something to, let's say, to a practical goal like this one. I also have my multiple security researches for Romanian banks. This is like as a hobby, let's say, just doing reverse engineering on different kind of attacks. What we currently have in Romania in the financial domain, so things like that. I'm also AWS community builder in the serverless niche from this year. So I'm more than honored to represent serverless and AWS at every conference through these projects. If you want to contact me on email or LinkedIn, if you have questions, ideas, proposals, anything like this, please feel free to contact me. So the story behind the research project, I've put here like some bullet points, just as a short resume, just as a short introduction into the project. Also, if you see here like research project, so it all started like a research kind of thing until it's like, let's say, a project. So starting with the first one, why the need for a high-performance earthquake notification system? I will tell you a story. Right now, what we have right now in Romania is like Romanian alert kind of notification system. I think this is also used in Spain and in other European countries. So it's like a convention between the European Union, and I think they are aligning to the same goal, to the same technical goals. But I saw some flaws, and also the Romanians, we saw some flaws in that application. For example, it's used right now to notify us at bad weather conditions, floodings, or anything like this, not earthquakes, just critical stuff that's happening. It's more like a, let's say, real-time notifications, but not early notifications. It's made by the Romanian government. There are some extraordinary people working there for that application. Nothing to complain, but it has some bottlenecks. We consider the bottlenecks are there because of the, let's say, large group of people. They need to inform like thousands, hundreds of thousands of people in different cities, in different regions. So it's very tough, although they have access to, let's say, to the underneath network level. So it's not like they're sending notifications through channels like in this project. They're sending the notifications like in, let's say, hardware level. Every telephone has this kind of application, and it's not something that you could download or things like that. You have the phone, so basically you also have this notification tool. So moving a bit on, we started some researches about how we could, let's say, upgrade this notification system, or what we could bring into the table for them, just as some ideas maybe, some updates, or yeah, just some discussions with them in what we could improve. So we started looking about what's about the earthquake notifications, what we currently have, and there is not so much, at least in our country. So we were just looking around after the data. So this is where the second question comes in: where to find good real-time earthquake data. I put here like good real-time data, but it's a difference between real-time data and early-time data. We found out later, and I will talk about it in the next slides. So we were just searching after some institutions, companies, government things, what they could provide us in terms of data, and after that, we built the entire system based on this data. I found out an institution, that's the Romanian Earthquake Seismic Research Institution. That's like part of the government of Romania, with some extraordinary scientists, engineers, had some very nice projects there. They are also working on some good projects. And one particular project was very interesting for us. Is called rapid notification alerts, in which they planted some systems in the southwest of the country, in Romania, where the seismic movement more intense, let's say. And through those systems, through those hardware systems, they are checking the movement in the ground. So just seeing if there is, let's say, a little movement in the ground, they will emit a kind of data into their systems, which are located near the stations, but also in Bucharest. Looking around into that paper from them, we also found out that there was, let's say, a challenge that was born from that research paper. Was about the kind of distance between the southwest of the country, so where the seismic movements are located, usually in Romania, that's the most important one, and the cities like the capital, Bucharest, or Cluj-Napoca, where I'm based, there is a kind of a distance, like in kilometers, 500, 600, things like that. But in terms of seismic movements and how the waves are coming from the specific area, we have like 1 minute, 1.5 minutes, 2 minutes until the full waves are received in the cities, in Bucharest, in Cluj-Napoca, and the other big ones. So when we saw this kind of thing, we were just looking around to see what we could do, like how we could send the notifications to a very large group of people in 1 minute, 1.5 minutes, 2 minutes. So that was our challenge when we found this real-time data, let's say early time data from now on. We talked about with them, also with the government, with the Romanian institution. We are retrieving their data and just trying to see how we could achieve a very interesting project, also to introduce some very interesting technologies in it, and yeah, we are in kind of discussion phase. So why choosing the serverless ecosystem? So I'm working with serverless for more than a couple of years right now, doing researches, integrations, like mostly with Lambda functions, queues, things like that, adapting the serverless in different kind of applications, mobile, web applications, and so on and so forth. But coming to this particular project, I was thinking that we need serverless because there's no need for servers. We don't need servers to be up and, let's say, up 24/7. We just need the servers when the earthquake is coming. We just need some things like some functions, some containers, which are like in a warm state and just prepared for when we need the infrastructure. But in this project, the earthquakes are like, I don't know, maybe once a year or something like that. So yeah, we don't need those physical systems, servers. Another one was the costs, because although the project is a very interesting one, it could save lives in the end. The government will not throw to us 1 million euros just because it could save lives. So we need to also control the costs, to control what we deploy as an infrastructure, to not have very, let's say, big bills, at least to control the costs, not to be like towards zero, but to have like a stable cost thing. Moving on to some technical stuff, this is the architecture of the first version. So the base kind of version. I will not talk about the gray ones because this will be explained in the next slides. This is basically the backbone of the notification system. I will talk about the rest of the components in here in the first version of the project, starting with the green one, in which we deployed like a web application for the subscribers, for the critical infrastructure guys, government guys, to be able to just register into the system and be able to be present in this database. Because this database, this Dynamo database, is basically the, let's say, the structure where we store the subscribers, the clients, all the information we need for this notification system to work. The application, it's mostly all of the APIs are in also using Lambdas, so just serverless things, API gateways. We are thinking to also include some kind of Kubernetes in here, maybe with some serverless Fargate. Currently, it's in research mode. And yeah, so some kind of load balancer to just keep the load balancing for the requests. A firewall, and that's about it for the green one. Talking about with the yellow squares, here we have the let's say error handling mechanism for failed events. If something is happening inside the first box, basically, I will tell you in the next slide this part. So this box, the first one is so-called Lambda Kafka producer, and the second one is so-called Lambda Kafka consumer. And basically in the middle, we have the Kafka cluster with the topics partitions. So the errors are mostly for, let's say, the failed event, the retrial mechanism for networking things, problems, latency problems, timeouts, anything that's not very critical. What's critical? It will be just sent through a queue. This is the dead letter error queue, and it will be monitored, and later on maybe manual, with some manual intervention studied. These two are for error handling. Moving on to the blue ones, we have the monitoring for every critical component. Like for the backbone of the system, we have the monitoring for the lambdas, for the also for the dead letter error queue to see what's happening there. Also for the Kafka cluster, we also monitor the costs for every part of the system that could have some increased costs at some point. Also the monitoring things for the SMS, for the mail. So these are the end channels, by the way. We are using in the first version like the SMS notifications, email notifications, just as a backup, and we are playing around with Telegram, but that's not very important. That's not our goal. Our goal is to send notifications through channels which, let's say, are more difficult to achieve. The purple ones, basically this one here in the lower screen is for a kind of a CI/CD pipeline for the backbone of the system, the notification system. We are based on the subscribers count. So just seeing how many subscribers do we have in the system, we could scale up and down the system. I will show in the next slides how we achieved this. Also updating the Kafka cluster, updating the part of the producers, part of the consumers. Through some code pipeline, we are using, like in this version, Terraform code for infrastructure as a code. So every part from here is like in infrastructure as a code, updated to a pipeline, let's say, and scaled up and down. What I'm meaning through scaled up and down, just as a high-level thing, you could see here some threads. You could see here some topics and some, let's say these are concurrency of lambdas, also warm state, cold state. These are the things which are scaled up, down, depending of the range of subscribers. In here with purple, we have the kind of code repository, some scannings into the artifacts, the build, scanning the code. We also want to scan the entire picture of the system, like with the roles, with anything that's inside the cloud. Also to scan this application, maybe we'll also have like a mobile application. So scanning the APIs, scanning all kind of things in that. This last one, the purple one, is for just maintaining the application, deploying the application, add code changes. If Kubernetes is the solution, probably we'll have like something Argo CD or anything like this, just to deploy the application every time at every code, at every version change, let's say. So everything should be in an automatic way without many manual interventions. Moving on to the gray section, this is the notification system in the first version that we had. So, like I was saying, we have this government institution from which we are retrieving the data, basically from their systems, which are in the ground. They emit the data into their systems or directly into our systems. We receive the data in the so-called Kafka producers, and we consume the data. This is, let's say, this is the brain of the entire project inside the same, let's say, inside the same architecture, and the Kafka topics with their partitions and so on. We used here some kind of multi-threading for the Lambda producers, just to use the full capacity, the full, let's say, the full resources from the Lambda instances. Also in here, we have some kind of multi-threading for achieving a kind of parallel, let's say, distribution and a parallel notification for the end clients. Some checks in here, magnitude levels. The government institution is also making some checks, so they are not, let's say, sending notifications if the earthquake is not like bigger than 4 or bigger than 5 on the Richter scale. In here, there's a custom topic roulette. We are thinking to just place a kind of randomizer to write the data, so the notifications in different partitions, in different topics, to not overwrite the data. Basically, this is the idea. In here, we have, like I was saying, the brain of the system, which orchestrates all the sending of the messages, how the messages are distributed to the end clients. And these Lambda functions are invoked as a, let's say, as a trick. We are invoking Lambda functions from the partition. So basically, every partition from the Kafka cluster will invoke and will trigger certain Lambda invocations, so some certain Lambda executions of code that will act on the subscribers in the Dynamo database. Also, it takes care of the SMS, mail, and Telegram notifications. The failed event kind of retry mechanism, the dead letter queues I was talking about in the previous slide. The architecture of the Kafka integration in the serverless context. So, like I was saying, we have this data from the institution. We are just sending the data from the producers, from the Lambda producers, through the multi-threading kind of technique into a kind of topic roulette, just to not write in the same partitions, in different kind of topics in Kafka cluster that will invoke the triggers. So you can see here the triggers for the Lambda invocations, code executions. So we are thinking at something that's trying to do something parallel in a concurrent way, because we need to achieve a kind of a speed. Like I was saying in the first slides, we only have like 1 minute, 1.5 minutes, 2 minutes to distribute the message to thousands of people, maybe hundreds of thousands of people in the future. So this was the current approach. using like parallel distribution, using Kafka, and using the most of it through the partitions of every topic, which are invoking the Lambda consumers. The Lambda Kafka producer key elements, I was telling you some things about the multi-threading in the Kafka producers. So we are using this one just to gain the most of the resources of the instances, to not waste anything for that. Using thread lock to not write in the same topics for separate threads. So we don't want to write in the same partitions, the same kind of information. We want, like in different partitions, to have different information, to not waste time in the end. Partition number, to not write data in partitions, like in incremental kind of number into the same execution. Using Lambda retry and SQS dead letter for the errors for both Kafka producers and for the Kafka consumers. The Lambda consumer key elements, here are some, let's say, tricks from this project, like this one, custom timestamp block mechanism. So we adopted something like a lock, because every invocation of Lambda was acting in some ways on the same items in Dynamo. So this was like sending the same notification to twice or third times to the same person, and another person will not receive anything. So that was not very good. This is why we implemented a custom timestamp block mechanism. If we see from an execution that the item was already, let's say, notified, processed, we are just marking the certain item with a timestamp, and we know at the future execution that Lambda invocation should not act on the same item. This is also the second one, optimistic locking in the custom Dynamo concurrency control. This is like an incremental versioning control. So for every item, if a Lambda execution acted already on an item, it will mark with a version that item. Using Lambda retry and SQS letter for errors, and Lambda consumers using cold start and warm start, we were thinking that in the part of the Lambda consumers, we need some kind of warm state. So we need some, let's say, containers which are already just running. If something is happening, if an earthquake is detected, we don't need to waste very much time. Moving on to the Lambda consumer, like integration with the database, and this is like the first version of the custom Dynamo locking. Like I was saying, the Kafka topics and partitions, like in that middle intermediate step, will act on different invocations, basically executions of code. So every execution of code, every trigger, will execute on different kind of items from Dynamo. Dynamo stores like the information of the user, information of the end client, which is with the ID, with the mail, with the telephone number, and so on. And we don't want, like I was saying, the same, let's say, the same invocation, the same execution to act on multiple elements which were already processed. This is why we implemented this kind of locking mechanism. So if the trigger from the topic 1, partition 1, already acted on the first item, the second one will not act on the same item, so therefore it won't notify the same person twice. This was the first version. We were thinking also with the versioning that was in the previous bullet point, to mark every item with a version and not notify again the same person. The custom Dynamo segmented subscriber processing, so the consumer part. Also, this is like improved kind of way from the previous one. We were thinking that, so in the previous one, we used like a simple loop, just looping through the subscribers, through the Dynamo list, and that was all with different kind of evocations. It had some speed, but yeah, not so what we wanted. So we came with this idea to segment the group of Dynamo clients, basically in groups of people. If you can view it, like the first version was, let's say, like a domino row, you can view the row from the front. And in this case, we are viewing like the row from the parallel in a parallel way, just acting with different kind of executions on different segments of items. So every segment will have like, maybe for example, in 100 people, we'll segment the list in 3 times. So we will have like 3 invocations acting on these 3 particular segments, just subscribing to just making the subscribers to be notified with those invocations. This particular one is a very interesting one, but we came to the conclusion that using just a simple invocation, just as a simple execution on a particular segment could be a little bit faster than the previous one, but also uses like a loop. So therefore, we came up with the idea to use like a multi-threading inside the same segment. So the execution will just asynchronous picking the items and trying to notify the subscribers in that particular segment, not allowing the next triggers, the next executions to act on the same particular segments again. So we have like also a different database where we store the lock ID from different segments. We calculate the segment size. So every time in like real time, we calculate how to segment the database, how many subscribers do we put in a certain segment, and how many like executions should we allow in a certain segment. This, by the way, it will be like in the next slide. That's more like an improved version of this one, where we are using like multiple executions. So we are allowing multiple executions into the same segment to notify the subscribers. This one will be achieved, like, for example, finding the minimum, maximum number of items, or calculate the segment size through different kind of Lambda separate functions. We will acquire the segment lock in that execution of code, which is in the consumer part, and process the segment in each execution triggered by these partitions from the Kafka cluster. And also we will release the segment lock after the item was processed. The next, let's say, upgrade, also in this area, I was saying about allowing multiple executions to be present on the same segment and to pick randomly and asynchronous elements from the segment and to notify the subscribers in a very random way. But again, keeping the idea in mind, like in the first kind of version, to not invoke the same item, to not subscribe to the same end client twice or many times. So we are allowing like multiple executions. We are controlling here the number of workers, basically the number of executions, which is linked to a certain segment of subscribers. And we are allowing a certain, let's say, level of maximum workers for each segment. This is, let's say, a very good way in which we could notify the subscribers, the end clients, in a more fast way, using the full capacity of the triggers, not having conflicts, not achieving race conditions and anything like this, and just allowing multiple executions, using the full capacity of how many partitions do we trigger and how many triggers do we have for the Lambda consumers, allowing them into making the work in these particular segments in here. Again, this find minimum, maximum for the total items, calculate the segment size, real time, maybe every 2 minutes or something like that, through different Lambda functions, acquiring a segment lock for a particular kind of segment. We will allow this, for example, in this one 5 times, processing the segment, start to the end. We will calculate how many items it's made it is making like a segment and releasing the segment log after the entire list was processed and the people were notified. We are currently in this phase, just looking around to see if we could also introduce some kind of caching mechanism or anything like this to keep in memory some subscribers or the list or the segment. So yeah, it's just currently work in progress. And yeah, in terms of auto-scaling of the system, I was telling you about in the first slide that we also want a kind of CI/CD pipeline in the notification system to not allow manual interventions, to increase different kind of critical parts with manual things. So this is why we came up with the idea to use like a custom auto-scaling to have like a stable range of subscribers for Dynamo and to create like a kind of a list of resources do we need after eye-looking, let's say, procedure. For example, just in the 0 and 101, we'll have 2 threads in the producers. So just using these kind of resources in the Kafka Lambda producers, we'll have like 2 topics in Lambda, maybe with 4 partitions, 2 partitions, something like that. And to provision concurrency for the Lambda consumers, basically how many Lambdas we will have like in a warm state prepared for orchestrating and notifying the end clients. And this gradually will be increased depending of these ranges, which are like manual ranges, but could also be more dynamic based upon the number of subscribers, the maximum number of subscribers. This is also done by a Lambda function. We'll have like an event bridge, just as a maybe cron job or anything like this. Every half an hour, every hour to see how many subscribers do we have in the system and scaling up and down the entire system in those particular elements of the system. This was achieved through some custom scripts, just some Python scripts, which are calling this SDK of the AWS, some APIs from the Kafka, and yeah, some custom code, API requests. This is like a sample for the custom auto-scaling, not so complex. We are just keeping an eye of the maximum topics, maximum concurrency of the entire system. And we are just looking around with that Lambda function to see if we need to scale up or down the entire system. Moving on a bit to a more, let's say, infrastructure as a code approach. So the next version, we also have this logic for having a Lambda and an event bridge, just studying how many subscribers do we have in the Dynamo database. A static kind of range in here with specific resources like number of the threads, number of the topics, number of the provision concurrency for the Lambda instances, the consumers basically. And we are using like Terraform for applying these kind of changes every time. Every time there is like a change in these static ranges, we are applying again the Terraform code through some GitHub pipelines. And there is let's say, a trick from us just to do a locals change in the GitHub repository achieves us to move like the entire pipeline, to start the entire pipeline just changing with the locals in here. Basically the locals are these kind of threads, number of the threads, number of the topics, number of the provisioned concurrency thing. This is currently the version we are using right now, using the Terraform, the GitHub Actions. We are also looking for some CDK kind of things, if we could achieve a greater speed also for the CI/CD pipeline. Also, as from a research perspective, just to see what's there and could be improved. This is the kind of change. Like I was saying, we are just changing the locals in the GitHub repository. We're just looking around to see if it's the same kind of content. If it's not, we are just triggering the pipeline through a file change. If a file change is detected, we will just trigger the entire pipeline. Basically, the Terraform code will be applied again. And the structure and the, let's say, the system will scale up and down based upon on this, if it's the case. Yeah. So basically, this is kind of it. We are like in a work in progress with this project, just discussing with the government of Romania to see what could we do more, just bringing up some ideas to the table, nice technologies from our perspectives. And yeah, we need to see what's next for us. But we will keep researching on this one. We have the data. We want to also gather some more people into the application just to see how it goes. We know that this is working, but yeah, of course, we didn't test for hundreds of thousands of people. But at least we want to have a target, like 5,000, 10,000 people. So probably somewhere in the future, the subscribing mechanism will be allowed for the civil population, or if they allow us for specific critical infrastructures. We don't know yet which is the best idea in this. So yeah, this is kind of all. If you have some questions, please feel free to ask them.
Yeah, sorry, I was coming without the mic, so
yeah.
Imagine that. Great talk, thank you very much. There are a number of questions, so let's see how many we can do. So many people are asking if you can explain the role of the topic roulette component, because Kafka cluster automatically spreads the data across different partitions, so what logic is implemented there to...
Yeah, we are thinking to implement like a custom logic, at least to not write into the same partitions, because we saw that using the same information could be into the same partitions in a certain moment of time.
So it's essentially an extension?
Exactly.
Okay.
A custom layer on top.
Yeah. All right. So then some other people are asking, like, okay, we saw that there are, as destinations, there are SMS and emails, but then you also mentioned something about network level notifications. And how does that interact from AWS, or how do you?
Yeah, so the government has access to this kind of networking layer. Maybe also in Spain is this networking layer. So you have the alert in your telephone. It's not like an application.
I see, okay.
Yeah, so we need to see if we could integrate with them at the networking level. Maybe it will be faster. We don't know yet.
When you say networking, it's like the 5G networking,
exactly,
no? The
something
okay,
like
I see.
Exactly.
All right.
Yeah.
Then there are a number of questions around using, of course, Lambdas and serverless. Have you seen problems with the latency, with cold starts, or do you have maybe hot Lambdas running all the time somehow to prevent, because time is crucial, so I guess?
Yeah, we are thinking to use these kind of warm starts, warm Lambda functions in the consumers, basically where we orchestrate like all the destinations, where we send the notifications to the client. So this is the major like area where we need to have the Lambdas prepared. Yeah.
Also related to Lambdas, like, how much data does the Lambda receive as input? Because there are constraints, so maybe have you suffered from that? Or
not so much, because the data is very little. It's like a message of maybe 20 words, or thing like that.
Not that much, yeah. Yeah, more questions. It's a long list. So people are asking, why did you decide to go with DynamoDB instead of, for instance, RDS for subscribers' data? Because it's obviously
serverless, maybe. Yeah. Exactly, yeah. In the first version, we were thinking to just choose Dynamo for having like the subscribers in there. It was the closest to us, but also on RDS, it's of course future. Yeah.
And also they're asking, okay, how can you be sure that it will scale quickly? Because obviously an earthquake is something that it needs to scale quickly. And not lose data in a high peak because of the...
Yeah, so like I was saying, we tested like for 500, like with our friends and things like that, but we want to embed like more people into the system, but we need like the allowance from them.
And do you do any load testing or to test the system, how quickly it can scale, or?
Just in those monitoring parts, we are just monitoring how fast the notification is received, sent, yeah.
All right, thank you very much. That was a lot of questions, but thank you, Vlad, for coming.
Thank you very much.
Romania, and thanks for this great talk.